This video is about the areas of parallelograms, triangles, and rhombuses. It's found in your text in section 11-2. Okay, we're going to start out with a theorem. It's the area of a parallelogram theorem, and it's somewhat surprising because the area of a parallelogram turns out to be the same formula as the area of a rectangle. But we have to define what we mean by base and height. So base, we can actually start with any one of the four side lengths. But once we pick the base, then we have to pick the height in a special way. So on this parallelogram, I'm going to pick the base length as this, which is also, as we've proved in class, congruent to this. So either one of these measurements would be the base. And then the height of a parallelogram is not this side. So don't make that mistake of thinking that this side times this side length is the area. For a parallelogram, we have to draw an auxiliary line that is perpendicular to the bases. It's perpendicular to both of these since they are parallel. So the length of this auxiliary line is the height. Okay, we're not going to go into a detailed proof of the theorem that gives us the area of a parallelogram, but I'll give you a sketch of a proof just so that you can have an intuitive idea of what it would be. So what I've done here is I've drawn the height as I just showed on the last slide, and then I've extended this line and drawn another perpendicular line here. And I've created a triangle here, and I'm going to call that triangle area region 1. And it would be pretty easy to prove that this triangle is congruent to this triangle, which I'm going to call region 3. And then this funny shaped area in the middle, let's call that region 2. So the area of the rectangle, so I'll say the area of the rectangle is region 1 plus region 2. And we know the area of a rectangle is base times height. I'm talking about this rectangle here. So the area of the parallelogram is region 2 plus region 3. But since we've already said that region 1 and region 3 are congruent, we can substitute region 1, the area of region 1 here. So we have the area of region 2 plus the area of region 1. And look, now we have an identical expression to what we had for the area of this rectangle, which is base times height, the formula that we already knew for a rectangle and we now know for a parallelogram. The next theorem we're going to do is the area of a triangle theorem, which you're probably familiar with, but I just want to refresh you on the ways that we can use this theorem. The area is 1/2 base times height. Now, what is the base? As with a parallelogram, we can choose any side of the triangle to be the base. So if I choose this side, AB, to be the base, then the height, to find the height, I would go to the vertex opposite this base, the vertex that's not touching that base, and make a perpendicular line going from that vertex to the base, and that would become my height. Now there are other ways that I could choose the base and height as well. So suppose that I wanted to choose side BC as my base. So I was going to use this as my base length. But notice that the opposite vertex to that base, it would really be hard to draw a line that's perpendicular to the base. If I drew a line something like this, it would not end up perpendicular to the base. So what I've had to do here is extend the base, extend that line, and still pick the opposite vertex, but draw a perpendicular line that actually is outside of the triangle, but it's still perpendicular to that base, and it still represents the height of that triangle. So we can choose any one of these three sides as the base, as long as we know how to form the auxiliary line that's going to give us the height. Okay, a brief intuitive proof of this would be to realize that the area of this parallelogram is base times height, the base being here and the height being here, and that the area of this blue triangle is half of the entire area. So we end up with the area of the triangle being half the area of the parallelogram, because we could prove these two triangles congruent by SSS. Then we have that the area of the triangle is 1/2 base times height. Okay, here's the area of a rhombus theorem, and we'll leave the proof of this as an extension problem. This is an interesting theorem because it has nothing to do with bases and heights. A rhombus, just to remind you, is a parallelogram with all four sides congruent. So it's kind of like a square that has been smushed over to the side. A rhombus is a special kind of parallelogram. If we draw the diagonals of a rhombus, then we can find the area of the rhombus using the measures of those diagonals. So the area of a rhombus is 1/2 times diagonal 1 times the measure of diagonal 2. Again, this proof is not very easy, so, well, it's not that hard either, but we'll leave it as an extension problem. Let's do an example problem. Find the area of an isosceles triangle with sides 10, 10, and 16. Okay, I'm going to make a diagram, which is always wise in worded problems like this. I'm going to have these two sides be 10, and the bottom side here be 16. Now I know from corollary 3, that wonderful corollary that's so useful, that I can drop a perpendicular line from this vertex and it will divide the bottom of this triangle into two equal parts, so that one part of this here is 8. Now I have a right triangle with a leg that measures 8 and a hypotenuse that measures 10. That reminds me of a 3, 4, 5 right triangle. So if you imagine a smaller version of this with 4 and 5, I've scaled this down by a factor of 1/2. This side would have to be 3. If I scale this back up, I find that this leg of the right triangle is 6. And that is going to give me the height of this big isosceles triangle. So I have that my height is 6. Now, the base that I'm looking for is not this 8. I just used that to find out the height of this bigger triangle. The bigger measure, the entire base of the isosceles triangle is what I'm looking for. So the base is still 16. So I have 1/2 base times height, and that gives me 48 square units. You try this one. Find the area of the figure below. Let's do another example. Find the area of an isosceles triangle with base 10 and perimeter 36. Oh boy, we know our base is 10, but they're not telling us the lengths of the other two sides. So I know that 36 must be the length of the bottom side plus something else, the other two sides here. But I have an isosceles triangle, and they're telling me that the base is 10, meaning that the base is not one of the two congruent sides. So I can divide up whatever's left over from 36, which is 26. I can divide that up equally because the remaining two sides must be congruent to each other. So I have 13 and 13. And let me just check that that perimeter adds up to 36. Yes, it does. Okay, so now that I know the measures of these two sides, I'm going to use the same trick again. I'm going to draw this auxiliary line that's perpendicular to the base. I know now that my 10 can be divided into two equal parts. So I have 5 and 5. Now, the right triangle that I'm seeing here, I'm recognizing as one of those magic Pythagorean triples. You might not have memorized this one, but it's 5, 12, 13. So I'm going to fill in the measure of this leg as 12 because I automatically know that, but you could find that from the Pythagorean theorem if you didn't know that triple. Okay, the 12 gives me the height of this triangle, so I know my height is 12. Again, my base is the entire base here, and that was 10. So I have 1/2 times 10 times 12, which gives me 60 square units. You try this one. Find the area of an equilateral triangle with perimeter 18. One more example. This time we're going to use trig to find the area of this triangle to the nearest tenth of a square unit. Okay, so I have a base of this triangle. I'm just going to write that in now. And what about my height? Well, if I pick the vertex opposite the base and I try to draw a perpendicular line to the base, I find myself just drawing this line, which is one of the sides of the triangle. So this is going to be my height. It's fine that it coincides with this leg of the triangle. In fact, that's always true when we have a right angle here. So I have a basis of 10 and I want to find my height so that I can find the area. And as you now know, I can use trig to find this height. So I have opposite, here's my right angle, here's my hypotenuse. I'm gonna just label that the hypotenuse, not so that this doesn't get confused with h. I'm not worried about the hypotenuse. I'm gonna ignore that. I need the height and I have this base, so I need the opposite leg and I know the adjacent leg to this 20-degree angle. So the appropriate trig function to choose is tangent. So I have that the tangent of 20 degrees is opposite, which is h, over adjacent, which I know it's 10. So I can solve for h. H is going to be 10 times the tangent of 20. I can look up the tangent of 20 here. I have 0.3640. So multiplying by 10, I just need to move the decimal over one place. So I have 3.640 is my height. Okay, now for area. Area is going to be 1/2 base times height. So I have 1/2, 1/2 times 10 times the height, which I've just found, 3.640. When I plug that into my calculator, I get 17.10. And the problem says I'm to round the area to the nearest tenth of a square unit. So 0.10 would round exactly, actually, to 17.1 square units. You try this one. Use your trig table or calculator to find the area of this triangle to the nearest tenth of a square unit. For further practice with this, see page 431 of your book, numbers 5 to 17 odd and 21 to 25 odd.